So 6.2, example 3, it says to prove the following identity. It's going to be a pretty typical instruction here in this section. All right, so what's step 1 for any proof? Yeah, drawing a line down the middle. And that's to keep you from cross-contaminating the two sides. Second step, pick the side on which you'd like to start. Which side is that? There is a correct answer to that. The left. It has more information because it has more terms, 2 terms instead of just the one on the right. And it also has fractions. So remember the strategy that we've already talked about is getting 2 terms into 1 term by getting a common denominator. So let's do that. You could do your crisscross applesauce, butterfly, multiply, whatever you want to call it. As long as you start in the top left, you can multiply from the top left down to the bottom right. And of course, 1 times that is just that. And then you take your middle sign, which in this case is plus. If it were a minus, you'd have to be careful because you have to distribute. And then it's 1 times that, which is just secant x minus 1. And then it's all over the product of the 2 in the bottom. So this will always give you a common denominator. It won't necessarily give you the least common denominator. And if it were a minus in between, then it'd be a little bit more fun. So as long as you start in the top left, it'll work if it's plus or minus. So that could be your first step. Now, if you look at the right side, which is your target, how are we doing? Are we making progress? Kind of hard to tell, right? But I'd say yes, because now we have 1 term on the left, 1 term on the right. That's looking good. But I need to somehow get rid of my secants and introduce cotangents and cosecants. So in the top now, what happens with your 1s? They cancel. And if you want to draw lines through them, that's fine. I just need to be able to see that they were there at 1 point. So I need to be able to see underneath your lines. And then secant x plus secant x is 2 secant of x. All right, now in the denominator, do you want to expand those out, yes or no? Well, if I leave them factored, it's so that I can divide out a common factor. Do I have a factor of secant minus 1 or secant plus 1 in the top? No, I only have 2 times secant, so nothing divides out. So if I leave it factored, I'm kind of stuck. So let's expand it out. Plus, you might want to do that because those are very special factors when you relate them to each other because those are whatjugates, conjugates. And when you multiply 2 conjugates together, you always get a difference of squares. And a difference of squares will then possibly set up a Pythagorean substitution. Possibly. All right, now if you compare it to the other side, look what happened. You got your 2. Heck yeah, we got the 2. The 2 is already set in stone. So I'm not going to mess around with the 2. I'm not going to call it like a 5 minus 3 because it's already good to go. So all I really have left to prove is that secant divided by secant squared minus 1 is cotangent times cosecant. All right. What would we do next over here? Secant squared minus 1. Yeah, that's a Pythagorean identity. So if you want to come off to the side and write it the way you memorized it, 1 plus tangent squared is secant squared. So secant squared minus 1 is tangent squared. So we have 2 secant of x over tangent squared. Now you compare it to the right side and you're like, yeah, I'm doing great. Now what? Very good. You can do a couple of things here. You can put everything on both sides now in terms of sine and cosine if you'd like, but it's kind of more challenging to kind of leave it on one side. If you notice, you need a cotangent factor on the right. You have a tangent squared factor in the bottom. Well, one of those tangent factors in the bottom is the same as the cotangent factor in the top, right? So here's what you could do. You could bring the tangent squared to the top and call it 2 cotangent times cotangent times secant. That's just kind of like using the reciprocal identity and the associative property of multiplication. I brought the tangent squared to the top and call it cotangent squared, but then I split it up. All right, so now I have my 2 cotangent of x, and so really all I have left to prove then is that cosecant of x is equal to cotangent times secant. Right? See that? How am I going to prove that? I don't want to just assume it. If you just go right to your final answer at this point, you're going to lose the check because it's not obvious. There you go. If you put it in terms of sine and cosine, you'll see that it works out nicely. So cotangent is cosine over sine, and secant is 1 over cosine. And now those divide out, and you're left with 1 over sine. What's another name for 1 over sine? Cosecant. So now you have 2 cotangent of x, cosecant of x. And is that what we needed on the right-hand side? Yes. So you can go ahead and sign off on it. Done. So that's just one way to do it. Again, you could have gone to the right, put it in terms of sine and cosine, and at any time put it in terms of sine and cosine on the left, and as long as the bottom lines are the same, you completed the proof. But it's a little more fun to try and stay on one side, although it's not required. So you're creating what you need. You're pulling out pieces that you already have, and you can kind of do it by divide and conquer. I got the 2, and then I got the cotangent, and then I was just manipulating the other stuff that was left. All right. Any questions on that one? Good morning. Oh, I'll let you read it. Yeah. Okay. So notice it says, adding to our list of algebraic strategies, eliminate complex fractions. Did we have complex fractions in the previous one? No. So let me kind of back up here. That's certainly one way to do it. Let's shrink-dink that one down. Okay. Looking forward to it. Some of y'all might prefer to do this right away. You go right to secant is 1 over cosine minus 1 plus 1 over cosine of x plus 1. So that could be your first step, in which case you would want to get rid of your complex fractions. So sometimes you might want to also remodel your straight line down the middle. If you do that, you have a complex fraction on each term. You can multiply by cosine over cosine. And this one you would also then multiply by cosine over cosine. And you can't do state change flip here because you have 2 terms in the denominator. So if you multiply straight across now, you get cosine of x on the top, and distributing in the bottom, you get 1 minus cosine. Plus up here you get cosine, and you get 1 plus cosine. So at some point, whether you do this first or like what we did, you're going to need to get a common denominator. And if you kind of did your crisscross applesauce here, it would also work. So I'm not going to finish that, but it works out nicely. But then here's what I would do. If I have everything in terms of sine or cosine on the left side, I would probably jump over here and write that as 2 times cosine over sine, and then times 1 over sine. And then if you multiply straight across, that's like 2 over 1. You get 2 cosine of x over sine squared. And then I would stop right there. And that becomes my new target on the right. Oh, we might as well finish it. Okay, if you get a common denominator now with your crisscross applesauce, you're going to distribute cosine times 1 plus cosine is cosine plus cosine squared. Plus, if you multiply diagonally and distribute, you get cosine of x minus cosine squared. And it's all over. If you multiply those out, you get 1 minus cosine squared. So that's expanding it as you get a common denominator, which is totally fine. I can follow you through that work. In the numerator then, your cosine squareds cancel, and you're left with cosine plus cosine, which is 2 cosine of x. And what's another name for 1 minus cosine squared? Sine squared. And now if you peek over at the right, are they the same? Yeah. So we're also done. It's another way to do the proof. It's just as correct as the other one. Just as correct. So, again, you're going to have several different options. You're responsible for finding one way. One way. And there's several different ways to do that. All right, example 4. Prove the following identity. Surprise, surprise. Draw the line down the middle. All right, so this one is already in terms of sine and cosine or independent variables t instead of x. Which side looks more complicated, though? They are arguably the same. They're both one term, and yeah, both sine and cosine. The only difference is they appear to be kind of flipped, but there's also a sign change. So in this case, just pick a side to start with. What side do you want to start with? The left side. The left side, okay. All right, so what do we do? We're already stuck, maybe. Remember, when you're stuck, put everything in terms of sine and cosine. Crap, it already is. Duh. Yeah, Tyler. Whoa, that accomplished. Yeah, I mean, it's better than doing nothing, right? If we started on the right, I'm not saying that this is necessarily the way to go, but it's easier to split up numerators than it is denominators. If you have multiple terms in the top, you could call the right side 1 over cosine of t plus sine of t over cosine of t. That's an option. And of course, then that would be secant of t plus tangent of t. But does that help us match it up with what it looks like on the left? No, that actually kind of takes us away from where we want to go, because the left side is still one term, and now we split it up into 2 terms. But just to kind of open your eyes to that possibility, you can split up numerators, but you can't split up denominators. So although that's legal, it's not going to be helpful. So maybe it's time for a new strategy. Is 1 minus sine of t equal to cosine of t by Papa Pid? No, because it's not squared. But man, if it were 1 minus sine squared of t, it would be great, right? Can I just do that? Just square both of them like that? That's legal. That doesn't change. That's not legal. You can only multiply by a clever form of 1. So here's a new strategy. We're going to multiply the top by a clever form of 1. And you can do this on either side. All right, so the first thing that I'm going to show you that makes sense is if I could get this to be 1 minus sine squared, I could call it a cosine squared, which would give me a cosine factor in the bottom like I want on the right. Well, how am I going to turn that into a 1 minus sine squared? I would have to multiply 1 minus sine by its what? Conjugate. That would be 1 plus sine of t. But if I do it in the denominator, I also have to do it in the numerator, because that is now equivalent to what? 1. So that could be one of your motivations. Multiply by the conjugate over the conjugate to set up a difference of squares, which would then become a Pythagorean substitution. That's one way to look at it. The other way to look at it is, okay, if I'm starting on the left, I'm going to go ahead and start creating the right side. So if you look at the right side, you're like, I would like a 1 plus sine of t to be in the numerator. So I'm going to go ahead and multiply by 1 plus sine of t in the numerator. But if I do it in the numerator, I also then have to do it where? In the denominator. So there's 2 powerful motivating factors that encourage you to do 1 plus sine of t over 1 plus sine of t. Okay, now in the top, do you want to distribute the cosine? No, because look over here on the right. We want the 1 plus sine of t to stay visible. So I'm just going to leave it in the top as 1 plus sine of t times cosine of t. And in the bottom, I'm going to expand that out and get 1 minus sine squared of t. And now what is 1 minus sine squared of t? Cosine squared of t, right? So multiplying by the conjugate over the conjugate sets up the difference of squares, which then sets up the Pythagorean substitution. And now we're almost there. If you look at the right side, I want the cosine of t to be gone from the top, and I want one of them to be gone from the bottom. Well, that's easy, right? Because I can divide out a common factor of cosine. So if one of the cosines divides out, I'm left with 1 plus sine of t over cosine of t. And it's easy. Conjugate over conjugate. It's a new strategy. Whenever you have something like 1 plus or minus a trig function, or a trig function plus or minus 1, or think about it as trying to introduce the right side, build up the right side, but you have to do it legally. Now, you could have done the exact same thing on the left side. Let me get rid of my EZ there and just show you what the proof would look like from the other side. Really, by the same argument, we're going to multiply this one by 1 minus sine of t over 1 minus sine of t, right? See that? That sets up the conjugates in the numerator. It also introduces the 1 minus sine of t into the denominator, which is what I want. So now we'll expand the conjugates in the top to get 1 minus sine squared. And on the bottom, we'll leave it factored because I want my 1 minus sine of t to be visible. In the numerator, what's 1 minus sine squared? Cosine squared, all over cosine of t times 1 minus sine of t. And now, very similarly, one of the cosines divides out, and we're left with cosine of t over 1 minus sine of t. And that is the left side that we started with. So in the end, on this side, they were pretty much equally simplified or equally complicated. And the key here is to recognize that you had to multiply by the conjugate over the conjugate. So that's the strategy. Keep that in mind. When do we want to multiply by the conjugate over the conjugate? When you have something like 1 plus or minus a trig function, or a trig function plus or minus 1. So there's two ways to do it, and they're both pretty easy if you know what to do. When you multiply by the conjugate over the conjugate, make sure you put your division bar in between there. Otherwise, you just have levitating symbols. That's like Chris Angel, freaky. All right, any questions on number 4? Let's summarize the strategy. Another strategy, multiply by a clever form of 1, that is the conjugate over the conjugate, which sets up a difference of squares, which then sets up a Pythagorean substitution. And then expand only the conjugates. If you notice what we did, we only expanded the conjugates, and we left the other side of the fraction factored. See that? We only expanded the conjugates, which was on the left side of the denominators, and we left the other side factored, because that's not a special product, and maybe then once you expand, you can divide something out. All right, example 5 then. Prove the following identity. Draw a line down der Mitte. Where to start, where to start? Left or right? Or right or left? The left? Okay. What would you do on the left? Oh, yeah, there's an opportunity right there. 1 plus cosine, you can multiply by 1 minus cosine over 1 minus cosine. Now let's think a couple of moves ahead. In the denominator then, that would give me a 1 minus cosine squared. And a 1 minus cosine squared would be a sine squared. So I'd have a sine squared in the denominator, which is the same as a cosecant squared in the numerator. Yeah. It wouldn't be illegal, but do I have cosines on the right side? No. In fact, I have a secant over here. I already have a secant over here. So although that wouldn't be illegal, I wouldn't necessarily do that as a first method unless there was a reason to do it. I would kind of save that until you get your stuck in. So in this case, kind of thinking just in your head where some of these things go, you can kind of see if it's the right path to take. You can like look at the map and see if it's going to take you where you want to go instead of walking down that path and being like, crap, there's a cliff here. I have to go back. So 1 minus cosine, but there could be fun in doing that, right? All right, so we're going to for sure expand the bottom. We get 1 minus cosine squared. Do you want to distribute the top? What I just said is typically you don't want to do that because something might divide out. You can always come back and distribute it. But for sure the bottom, you're multiplying by the conjugate deliberately so you can expand the conjugates. 1 minus cosine squared is a sine squared. Now, if I leave the top factored, am I going to be able to divide out a sine from either factor in the top? No. So that's not going to be worth leaving factored. That's the whole reason we leave it factored, is so we can possibly divide something out with the sine squared. So in this case, if nothing is going to divide out, guess what we could then do in the top? Now we can distribute on this line, but we kind of held off on that. Secant times 1 is secant minus, what's secant times cosine? This is another one that you can know. It's 1. Because how are secant and cosine related? They are reciprocals. They're reciprocals. And what's anything times its reciprocal? 1. So cosecant times sine, tangent times cotangent, and secant times cosine are equal to 1. That's kind of worth knowing. They come from the reciprocal identities. So you can just call that 1. If you know that, you can call it 1. If not, write it as cosine times secant, and on the next line, put secant in terms of cosine. That's when you would want to do that, and you'll see that it equals 1. So some of these things you pick up as you go. And now we're almost there, right? I want secant minus 1 as a factor, so all I have to do is use the reciprocal identity. 1 over sine squared is the same as cosecant squared in the top. And we're left with secant of theta minus 1. And it's also easy. And fun when you know how. So don't think that you have to do too many things in one step. Include more steps if you need to, and just do one little thing per line. You just have to rewrite everything the next line. You work down one step at a time. And I would again say, when in doubt, don't leave it out. Show more steps rather than fewer steps. But I'm with you. I can follow that a secant times a cosine is a 1. That's what I would consider a relatively obvious one. Okay. What if we started on the right-hand side? You want to see what that would look like? Well, if I were starting on the right-hand side, what I would probably do is everything that I did here backwards. I would bring cosecant squared to the bottom, call it sine squared. Bless you. I'd call sine squared 1 minus cosine squared. And then I would realize that 1 minus cosine squared is the difference of squares, and I would factor it as 1 minus cosine times 1 plus cosine. And then what I'd probably do is write secant as 1 over cosine and get rid of the complex fraction, and it would also work. So there you go. Conjugate over conjugate, kind of a nice little strategy. It works well a lot of the times. So here's yet another strategy. Do any quote-unquote obvious math. Why is obvious in quotations there? Is that what someone said? Am I quoting a person? No. It means do what's obvious. Because it may not be obvious to someone what is obvious to someone else. So what does it mean? It means do anything like distribute, factor, combine like terms, divide out common factor. That would be what I would consider quote-unquote obvious. Okay, how about number 6? Guess what the instructions are? Prove, yeah. Ooh, what variable is that? Phi, yeah. Yeah, sometimes called phi. Usually phi. Not fo or fum, though. That's different. Phi. Fo, fum. I smell trig proofs. Let me have some. Yeah. Beautiful straight lines. Some of y'all make awesome straight lines. How do y'all do that? There we go. Thanks, Notability. Okay. Which side do you want to start on? I heard right and I heard left. Heard right and they're both correct, actually. They're both right. The left is right and the right is right. They're both right. Because ultimately, there's no wrong side on which to start. Some are just easier than others. You want to try that again? Oh, yeah. Okay. So on the left side, we have a opportunity for conjugate over conjugate. 1 minus cosecant, 1 minus cosecant. Over here, we have some obvious math we could do. Now, if you distribute on the right side, notice you are going to break up a one-term dude into 2 terms, yeah? Just be aware of that. And on the left, we still have 1 term. So maybe start on the left. It's worked twice in a row. Let's see if it works again. We'll multiply by the conjugate of 1 plus cosecant, which is 1 minus cosecant of phi, 1 minus cosecant of phi. All right, so for sure in the bottom, we're going to distribute or expand. We're going to get 1 minus cosecant squared of phi. And in the top, we'll just leave it factored 1 minus cosecant of phi times cotangent squared of phi. All right, so the whole purpose of doing that is to set up a Pythagorean substitution. So here's where you want to be careful. We memorized it as 1 plus cotangent squared of phi equals cosecant squared of phi. So what is 1 minus cosecant squared equal to? Not cotangent. Negative cotangent squared. If you bring the cosecant across, you're going to have to bring the cotangent squared across, and this becomes negative cotangent squared. That's why I would always recommend writing those dudes out to the side so that you can physically adjust them. Because if you're off by a negative, you're going to be very, very frustrated. It's like taking the wrong route on the map. And I have 1 minus cosecant of phi. So see why we left it factored? What are we left with in the numerator? If I still keep it factored, what happens with your cotangent squared of phi's now? They divide out. Sweet. And I'm left with a negative 1. Now, dividing by a negative 1 is the same as doing what with a negative 1? Multiplying. So what I'm going to do now is on the next line, I'm going to go ahead and distribute the negative 1 into both terms. So it's going to be a negative 1 and a positive cosecant. So I'm going to write that as positive cosecant. I'm going to flip them around, and a minus 1. That negative can cause you a lot of grief if you treat it, casually or you forget about it.
Students, please from this interruption.
Now what?
Anyone who signed up for the blood drive around 9 o'clock, please make your way to the library at this time. We do need to keep on schedule for the blood drive. Also, teachers, just a reminder to hand out progress reports today during third period. They are in your teachers' boxes. Thank you.
This is where I would probably now jump to the right side, simply because my left side is so simplified, there's really nothing obvious left to do except to put it in terms of sign. 1 over sine minus 1. Whereas the right side is not even in terms of sign, but now there's some obvious math to do. I'm also going to notice that now I do have 2 terms, bless you, which when I distribute on the right gives me 2 terms. So here's a good one where jumping to the right side is really kind of the right thing to do. Now when you distribute, you get that. What is cotangent times secant? I'm not sure. So as we've already seen today, if you put it in terms of sine and cosine, you get that. And of course, what is cotangent times tangent? We already talked about that. It's 1, because cotangent and tangent are reciprocals. So what happens in the first term? Your cosines divide out, and you're left with 1 over sine, which is what? Cosecant. So you're left with cosecant of phi minus 1, and now you are smiling. There you go. So here are the kernels to extract from this problem, and we'll call it the day. We didn't do this, but you could change the variables if you don't like the given ones. You just got to do it in the beginning. If you don't like phi, just X them out. Say, I don't like you, phi, and X it out. Now you have X. That's fine. Work on both sides and quote-unquote meet in the middle. That's the song title. That's why that one's in quotes. All right. We're going to pick up with example 7 tomorrow and look at the instructions. Prove the following identity. We'll finish the notes tomorrow as well. So be working on das Workensheeten. Don't let it sneak up on you. Don't let this one sneak up on you. Yes. Have a great day.